Planetary magnetism is one of the most fundamental aspects of planetary science because if a planetary body has or ever had an internally generated dynamo field, then that immediately tells you a lot about its deep internal structure and early thermal history. It tells you that the interior got hot enough for the metals to segregate out from the rocks, and that the motion of that electrically conductive deep interior was vigorous enough to generate a dynamo field. Now, the case of the moon is interesting because unlike the Earth, there is no global dynamo field operating on the moon today, and yet there's parts of the crust that are magnetized strongly enough to be detected from orbit. So how do you magnetize parts of the crust without a dynamo field to do it? Well, one possibility is that those rocks were magnetized during shock events, during impact events. But another possibility is that there was a dynamo field operating early in the moon's history at the time that those rocks formed, and that the dynamo field has since turned off. And so understanding those crustal magnetic anomalies is an important part of understanding the history of the moon. So something else that's uniquely interesting about lunar magnetism is that many of these crustal magnetic anomalies are accompanied by these strange-looking optical features known as lunar swirls. So this is really amazing, right? Because you can see optical evidence of magnetism on another planet, and if you know where to look, you can actually see this one from your own backyard. These lunar swirls are optical anomalies that are co-located with many of these crustal magnetic anomalies on the moon. And what we think they are is that they're places where the presence of those strong crustal magnetic fields is interfering with the way the solar wind plasma, which is a stream of charged particles that are coming from the sun, the way that plasma is accessing the surface is being interrupted by the presence of that magnetic field. And that leaves optical marks on the surface that essentially track and tell us the structure of the near-surface magnetic field on scales that are much finer than what we can resolve with the orbital magnetometer data. So this allows us to put tighter constraints on the structure of those underlying magnetic source bodies, which allows us to put better constraints on their origins. Okay, so the idea here is that we're going to use the length scale over which these swirls, these bright and dark markings, transition between the brightest part of the swirl to the darkest part of the swirl. And we're going to use that bright to dark transition length scale as a proxy for the length scale over which the near-surface magnetic field transitions between vertical and horizontal. And we have some idea of the surface field strength, and if we have that constraint from the length scale from the swirls, that allows us to explore a range of parameter space, different possible structures for the underlying magnetic anomaly. And what we find is that what's really important is the depth. By far the most important factor is the depth. Now that part of that's obvious because as the source gets further away from the surface, the resulting surface field strength is going to be weakened. But what's less obvious is that in order to preserve that bright to dark transition length scale, the source, as it becomes more deeply buried, has to become increasingly compact. If you'd like to learn more, please come to my poster on Tuesday morning at AGU. I'm Doug Hemingway. I'm a planetary scientist at the Carnegie Institution for Science in the Department of Terrestrial Magnetism.